Alright, so what does a piecewise function sound like it is?
Pieces.
Pieces that make up a
Function.
function. Okay. Context clues. You know, we can break it apart. So it is going to be a function made up of two or more other functions over specific intervals. So it is a function. So we do use function notation. So f of x equals. And then it's going to get a bracket. Okay, it's like one of those squiggly brackets, you know, the fancy bracket. And then you're just going to have a list of a bunch of different pieces of functions that are like listed. So we have like x squared, 2x plus 1, the square root of x. Those are different pieces, okay? They're different types of functions. And then listed over to the right are going to be what we call your intervals or your restrictions. So basically we could say that my first piece I'm going to use when x is less than 0. My second piece I'm going to use when x is greater than 0 but less than 2. And my last piece I'm going to use when x is greater than or equal to 2. Okay? So basically you have a list of functions and then the intervals that you use for each one of those functions. Now this is our piecewise notation. So for your project, it is a piecewise project. So you're going to be creating a piecewise function. So you're going to need to use this notation. Okay? Because I usually get a couple of people that don't use the correct notation, okay, on their project, and then you don't get full credit. So just make sure as you're writing out your function, you need to put it in this format. Does that make sense? Yes? So how many pieces does that function have? 3. What's the smallest number of pieces I can have? 2. Because if there's only 1, then it's just a function. Yeah. Okay? Is there a maximum number of pieces that I can have? No, there's actually not. Okay? However, on your project, you will have to have at least 6 pieces. Okay? Alright, so let's look at an example. So, it says evaluate the function when x is -1, 0, and 1. So normally when we evaluate a function, what are we doing? Not solving, that's different. Plugging numbers in, agreed. That's what evaluate means, to plug numbers in for x. Except this time, how many equations or pieces do we technically have? 2. Do I want to plug it into both of them and get out 2 different y values? Why not? What happens if I get out 2 different y values from plugging in one x value? It's not a function, right? That's what the definition of a function is I can't plug in the same x value and get out 2 y values. Agreed? So that means that we have to pick which piece we want to plug into. And that's where these intervals or restrictions come into play. So if I'm looking at f of -1, which of my restrictions or intervals does -1 belong in? The first one or the second one?
First one.
The first one. Do we all agree that -1 is less than 0? So that means that I'm going to plug it into the first piece. So I would have -1 squared plus 1, which gives us 2. Are we all okay with that? Now, notice that 2 is not in my first interval, but that's okay. Remember, 2 is a y value, not an x value. So the only part that has to be in this interval, x is less than 0, is whatever we plug in. Whatever we get out, it could be 1,000,000, it could be -200. It doesn't matter what we get out. The only part that we care about for the interval is what we plug in. Questions on that one? Okay, so looking at our next one, we have f of 0. Which interval do we want to use to plug in for 0? Why the second one? They both have a 0 on them. Because it has the equal to bar. So how many functions, or like lines, can have the equal to bar for the same number? So what would we do if both of those had an equal to bar? If I plugged it into both of them and I get out different numbers, is it a function still? So how many of my functions can have an equal to bar? One of them. Yes? So notice, like on my last one, only one of my zeros had an equal to bar. Only one of my 2's has an equal to bar. For your restrictions, only one of your lines can have an equal to bar for the same number. Okay? So, we said I'm going to plug it into my second one. So, what do we get? -1. And then lastly, we're plugging in 1. Which one are we plugging it into? The second one. And we get 0. Do you have any questions on that? No?
I'm kind of
I do understand that.
For some reason, I keep like coming in and out of reality. But like when I'm in reality, I pay attention. I get restrictions, but like I don't know what we're doing or what it's called, but I understand that. So fun. First one.
Alright, so let's have you try one on your own. Okay, so you have a different piecewise function. This time you want to evaluate at 0, 1, and 2. Yes, correct. Did we get anything? So turn and check with your neighbor first. Turn and check with your neighbor, see if you got the same answer.
They got the same.
So either you're all wrong or right. So if I plug in 0, which piece am I using? My first or my second?
The first one.
The first one. And what do we get?
0.
0. On my second one, which piece do we want to
The
use?
second one.
The second one. And we get 3. And my last piece, or function, which one do we want to use? The second one, and we get,
See, I knew it. This is not
Yes.
hard. Why is this not hard?
This is so good.
Yeah, why-
Why isn't
alright,
this
so
hard?
that's evaluating a piecewise function, okay? So what your project is going to be over is then using those to graph.
Oh,
Yeah,
this
there it is.
is
Thank you.
Wait, so like you unblock the points.
Okay, so what we're gonna do is notice again. Bring it back in. We said that these are each individual pieces, and so basically what's gonna happen with our graph is it's gonna be a bunch of like pieces of other graphs. So first we're just gonna graph each of our pieces by themselves. So on my 2x plus 3, okay, that's my first piece. If we were to just graph that normally, what would that graph look like?
2x plus 3, 2 is the slope,
Uh-huh.
and y is 3.
Agreed.
a y.
Y-intercept.
And
Oh
then
my
just,
god, I remember.
yeah,
Way to go.
That's what.
like algebra.
I've got y equals an x
Let
plus
him
b
have a
inverted. Yeah, let me have my moment, Shelby. Jeez.
So we get a graph that looks like that. Agreed.
And you do this similar thing to last night.
So what is that graph gonna look like?
The slope is
Negative.
negative 1,
Uh-huh.
and the y-intercept is 4.
Uh-huh.
Oh my
Yeah.
god.
You go.
You go, girl. And then, don't you like plug in the exclamation?
Not quite.
Just kidding.
We're gonna look. It has to do with our x intervals here in a second. So as it is, if that was like where I stopped, okay, is that graph a function?
Yes.
No.
For both of them together. Each of them on their own is a function, but together, is it a function?
No.
No, because it doesn't pass my vertical line test. Agreed?
Yeah.
So that's where these intervals over to the side are going to be important. So, my f of x graph. If I'm just looking at my orange graph, okay, notice that our restriction is x is less than or equal to 1. So I'm going to go to an x value of 1, go up to my orange graph, okay, this is the point that it's at. So then we need to decide if it's going to be less than 1, is that going to be the portion of the graph that's to the left or to the right? To the left. It's less than. So that means that this is the portion of the graph that I would want to keep. Normally I would just like erase the rest of the graph, but I want you to see like where I'm getting them from. So for this part, I'm just going to draw it in blue. Okay? Now we have to decide at 1 though, does that graph get a closed circle or an open circle? Does it have an equal to bar?
Yes.
So if it has an equal to bar,
Close.
then it has to be closed circle.
I'll remember that.
Okay? Now for my red graph, again, this time where x is greater than 1. So I'm going to come up to my x value of 1, go to the point that that's at. Do we want the part of the graph that's to the left or to the right? We want all of that stuff.
And then it's going to be an open circle.
This
So
time
then
it's
you
going to be
switch
an open circle because we don't have an equal to bar.
So then you
Oh,
should.
wait.
No, we don't have to shade. You would just like erase the other two parts that like stick up.
Last year we basically like would color one color and then
Oh,
color a
this is
different
when we
color
have
and then like the portion that it would meet, like the two colors would meet.
Sure, that's a different.
Are we gonna have to shade?
Because again, guys, this isn't an inequality. So remember, an inequality would be if I had 2x plus 3 is greater than 1, right? That's then when you would either shade above or below your graph. Okay, this is not an inequality. This is just where my pieces start and stop. Does that make sense?
Piecewise function.
Piecewise function. Okay, so let's do another one together.
Specific.
What?
After we did that, is it a function?
Yeah, because just my blue pieces would be a function because they don't overlap. So on this one, I have x squared. Okay, what does my x squared graph look like? It's a parabola, and it goes through 0, 0, right? And then it also goes through 1, 1, negative 1, 1, and it's like our U shape. Agreed? But notice my restriction is x is less than or equal to 1. So I'm going to go to 1, the point that I have there. Which part of the graph would I want to keep?
The left.
The stuff that's to the left. So this time, I'm just going to erase the part of the graph that I don't need. Okay? And then at 1, do we want a closed circle or an open circle? We want a closed circle because we have an equal to bar. So that would be my first piece. Then my next piece is 2x plus 1, which is a line. What's my y-intercept?
1.
1, and we have a slope of
2. Ghosts.
So it would come down like this, but where is that graph going to stop?
When you get to the race.
At 1, right? Because we only want everything that's after 1, so to the right, okay? So I wouldn't need to keep filling in because that's where it would stop. So I'm going to erase that intercept. And then, do I want an open circle or a closed circle at 1?
Open.
Open. And so that would be your graph.
Why is it
So
still
it can
easy?
be pretty random when it comes to these, or
What do you mean?
I'm just saying
I don't know what's random.
like the different equations.
Correct. Like you could have square roots, you could have just absolute values, you could have x squared, x cubed, whatever the pieces are.
So we really need to know what's what.
Correct. That's why we looked over our transformations and our parent graphs because we need to know how to do those to graph each individual piece.
Is this?
Just that.
Just this?
So for piecewise functions, okay, these are functions now, agreed?
Yes.
But is that a continuous function?
It stops at a certain.
No.
Yes.
Can I take my pencil, draw the entire graph without picking it up? No, because at 1, right, I'd have to pick my pencil up, go to the next spot, and continue on. So I have a hole in my graph. Agreed?
Yes.
Uh-oh.
So is it continuous?
No.
No, it's not continuous. So sometimes we're going to need to figure out if something is continuous or not without looking at the graph. Okay? So what would make it continuous? If they connected, right? If my two pieces meet up at the same spot?
Yeah.
Agreed? Now, where do they have to meet up at the same spot? Like at which values? So like on our last one, where did we need these two to meet up at? At 1, because x squared is going to be continuous. 2x plus 1 is continuous. The only spot that's going to be like an issue is where we switch from one to the other, which was at 1. Agreed? So notice here I have x squared. My next one I have negative x plus 2. Where would those need to meet up? At 1. Agreed? So then for my second and my third piece, where would those need to meet up? At 2. Okay? Now, how do I check and see if they do meet up or not? Why? I'm not saying you're wrong, I'm just asking why.
See, they equal each other. Like.
Why are we wanting to see if they equal each other? What value does that give me by plugging in 1?
Why?
Your y values. Because if my y values are the same, right, and I'm plugging in the same x value, that means they have to meet at the same point. We agree? Okay. So if I plug in 1 to my first piece, what do we get? Just 1. If I plug in 1 to my second piece, what do we get? Do those two things equal each other? Yes. So 1 equals 1. So it works. Okay? So that means my first two pieces meet up, but if I have multiple pieces, I have to check that my next pieces also meet up. So what do I want to plug in this time? 2. So I would have -2 plus 2 gives us 0. Then on my next one, we would have 4 minus 6 plus 2,
Which is 0.
which is also 0. So do those two meet up? And then we also have a 0 and a 3, but there's not pieces on either side of them, so those don't really matter. That's just where my function starts and stops. So is this function continuous?
Yes.
Yes. Does that make sense? So, on your project, your function is going to have to be continuous, which means that you're going to have pieces that meet up. And part of the project is showing me that they do meet up. So, doing these steps, plugging in 1, plugging in 2. Now, if I got, say, 0.999 and 1, is it continuous?
Yes.
No.
Are you kidding?
No, I'm not kidding. Or if I got 0.0001 and 0, is it continuous? No. You cannot round. They have to equal exactly the same value. Did you have a question?
Yeah, is the project going to count as like a daily assignment grade or
The
Uh,
quiz
ninth
grade.
grade.
The quiz grade.
Nice!
Okay, so on my next one, what value do they overlap at this time? 2. So what do we need to plug in?
2.
2. So what do I get for my first piece? 2 minus 1, 1 squared is 1. Okay. What about for my second piece?
4.
Do those two things equal each
No.
other? So is this continuous?
No.
No. But notice the second part of our instructions. Say if it's not continuous, we need to change a value. Now, remember, okay, yesterday, the last part of our notes, remember we talked about finding A values that stretch or compress our graphs? Do you remember doing that?
Yeah.
Yes? So, notice, okay, if I were to stick an A value out in front of my first piece. Go with me? I'm only changing one value. I'm changing the number 1 to something else. Okay? And I want to make it equal 4. Yes? Because that's where my other one is at. So I want my Y value to be 4. And then what X value do we have to plug in? 2. So what is 2 minus 1? Squared is? So we get that A is 4. So if we made our first piece 4 times x minus 1 squared, well now my function would meet up and it would be continuous. Yes.
Did we get our 4 from the other equation?
Correct. Because I need my y values to be the same value, so that's why I had to set it equal to the y value we got from the other one. And again, whenever you guys are doing your pieces, sometimes you might have to switch your a values so that your pieces meet up. So that's when you want to set them equal to the same thing and solve for whatever your a value is going to be. Questions?